All right, people out there in the internet, try and solve these. Sure glad I unpaused for that, right? How to do this. I'm not going to write every answer. You should definitely be able to answer these. So here we go. They'll be somewhere. All right, the boiling point of water, which is H2O, ammonia, which is NH3, and methane, which is CH4, are that, and that, respectively. So why would water be so high? Hydrogen bonding and dipole-dipole bonding, right? It's a major part. All right, so that's water. Now let's skip over NH3 for a minute. Why would this be so low? It only has LDF only, and it's a really small substance. Is there hydrogen bonding? Someone's going to put it. Is there? No, because it's not FON. Okay, so then this one's the tricky one in the middle. Does it have hydrogen bonding? Yeah. Is it polar? It is polar. But it's not as polar. It's significantly less polar than water. But polar is polar. So that's kind of why it's in the middle. And it's pretty low comparatively, but it's in the middle. Water, very polar, lots of hydrogen bonding. NH3, not very polar at all, but it is a little bit, and smaller or less significant hydrogen bonding. And then CH4, just LDF, and that's it. All right, we talked about this yesterday. Chlorine, bromine, and iodine. They're not bonded with anything except for themselves. So there's no option except for what type of forces? LDF. It happens. I've said it on accident before. All right. There you go, sure. All right, so London dispersion forces are the only thing. So what's the difference between chlorine, bromine, and iodine? We said it yesterday. All right, size and number of electrons. The more electrons or the more massive you are, because they go together. Okay, yeah, true. The greater the intermolecular forces. Sorry, I was distracted by two beautiful bears. That's the cutest thing. I know what would make them cuter if I never saw them again. I'm sorry. That was rude. True, good point. My fault. Okay. No, we're good. Okay, here. Propane is a gas. Ethanol is a liquid. Propane, barbecue stuff. Ethanol, you see that in two places. That's the E85. That means that's the 15% of stuff they can put in cars. This is also drinking alcohol. No. It's
a base.
Yeah. This stuff just technically is called denatured alcohol. So they've made it a little less dangerous by mixing it with other things when you actually ingest it. But if you were just to drink straight ethanol, you'd be in trouble, big trouble. Okay, so what's the difference here? It's just CH, but then OH. All right, this one is both somewhat polar and has hydrogen bonding. But then propane only has what? LDF, which are the weakest.
So if it's a more complex molecule, but it does have something that would be hydrogen bonding, it counts as hydrogen bonding.
Yeah.
I have a question, David.
Yes.
Doesn't ethanol also make those ones that we were talking about that are more like the lines rather than the circular one? Or did I mix those up?
Yeah, they both
I
can.
don't think that's as important as hydrogen
Yeah,
bonding.
they both can. This stuff, there's something Tolman asked me about before called cyclopentane or propane. So this could be a circle as well, but usually We don't put it that way. We just go straight line.
So the cyclopropane should be C3H6.
Yeah, it'd be a 6. So anyway, those are the main ideas on how to answer that. We should be at a point now in our discussion where you could give me a decent explanation about this. Now, in a week or so, you should also be able to explain these. Definitely.
So, with just saying the size and number of electrons, is that all we need to say?
Well,
Or should
you
we
should
expand a
definitely
little
say since ethanol is polar and has hydrogen bonding, it would have higher intermolecular forces.
intermolecular forces, and then we don't need to say which would
You can,
you can.
which would make it have a,
But you don't need
this
to.
would be, yeah, a higher boiling or melting point, whatever you wanted to say. If you can tell them it's the size and how it affects the intermolecular forces, that's pretty good. All right, so
On the AP test, do we need to say every reason why, or do we just need to say at least
you
one?
just need to give a solid explanation. Judah, hit that bottom line. I know, like, because that's a hard answer. If you give a short sentence, they're not going to like it. If you give a paragraph, they're not going to like it. They want you to be concise, but cover it. They're looking that you know that the size, the number of electrons are difference between those two things. And so then you would add, so iodine has higher intermolecular forces than chlorine and bromine, something like
Would
that.
work?
It worked great.
Combine one that has higher IMF work.
If you say the size causes it to have higher IMF. Are you all right, Ellie?
Yes.
Okay. Okay, this is in your book somewhere. Make sure that you kind of understand this idea. So it's just a flow chart here of figuring out something. Are there ions? Yes. Are there polar? Yes. Then there's both. No, then it's just an ionic bond, like a salt crystal. This would be like salt water. All right. Then if there are no ions, then you ask next, are there polar things? If there's hydrogen with NO and F, it will have both hydrogen bonding and dipole-dipole. If there are not, then you only have dispersion or London dispersion forces. Okay, this chart's pretty good. Sometimes I don't like the charts that the book puts together, but it's pretty good. Was that on the notes I was messing around with last night? Okay. That was fun. There's just something rewarding about writing on that screen with that nice pencil and like just things create. I liked it. And I know it's nerdy. Most people get a new iPad and they play a game on it. I thought, let's write notes for chapter 11.
It looks satisfying.
It was satisfying. All right, here we go. I'm going to go fast. Grace is my friend.
What is a slander?
They can't slander. I know your family, so
That's true. You do know my
I know your
The
roots.
only thing you could slander Grace for is her hate for poetry.
Yep.
Those are your roots, Grace.
I don't like poetry either, so
Perfect.
Why didn't
Next.
you teach poetry in school?
I don't know.
Amen.
Moving on.
And I memorized the
Intermolecular forces affect many physical properties. So we know about them, but we definitely need to know this. The strength of the attraction between particles can greatly affect the properties of a substance or a solution. For example, it will affect viscosity, which we don't really worry about that much in chemistry, but it's how well it pours. Resistance of a liquid to flow is called viscosity. It's related to the ease with which molecules can move past each other. Viscosity increases with stronger molecular force. So a high viscosity means it does not flow very well. So this would be like cold molasses. You tip that over, you come back in 6 months and it's finally drained out. All right, so the greater the intermolecular forces, the greater the viscosity. But if you can heat it up, then the viscosity increases. That sort of should make sense. The warmer you get it, the more it moves to the liquid or gas state, and those obviously move forward. You don't need to worry about numbers, but just kind of the application here. The larger the molecule, the greater the intermolecular forces. There you go.
molecule.
What's that?
How viscous is
I don't actually know the viscosity of water, but hexane is probably less viscous than water. So just a factor of 10. It's not, I mean, that's kind of a big deal, but not a huge deal.
So
Said in
IMF,
the,
I was just gonna say IMF is directly related to viscosity then.
Yeah. All right. I don't know what you guys called these growing up, but
What even is that?
this is a skeeter or a Jesus bug.
Oh,
A Jesus
I
bug?
like it.
I call it water spiders, but okay.
Water spiders. Okay, here we go.
I call it water.
Surface tension.
We don't have those in Minnesota.
Yeah, you don't. Surface tension results
Then in that
Have a
case,
difficulty
from the net inward force experienced by molecules on the surface of a liquid. Why do people talk when they talk? So the liquids actually pull towards each other. All right, which means if I put a pressure here to go past them, I have to force them apart. Now, that's not very hard, but if you hardly weigh anything and you distribute it over 1, 2, 3, 4, 5, 6 legs, you can walk on water. All right, so surface tension. Next, phase change. We'll talk a lot about this, but the intermolecular forces definitely affects phase changes. So you don't have to write all this out. There's a better chart in my opinion. We'll get there in a second. But we're going to talk quite a bit for the next 5-10 minutes about phase changes. It's when we go from a solid to a liquid, which hopefully all of you know that means a liquid. When we go from a liquid to a gas, which we say is boiling, but technically it's vaporization. It's when the liquid turns into a gas. All attractive forces in the liquid are broken and they're converted to the gas state. Now, in reverse, we have a gas going to a liquid. That is condensation. I was so proud of my kid. He said the other day that, I'm like, how did school go? He's like, I was just really frustrated. I'm like, why? It's like, because my teacher said it required heat to cause condensation. And he's like, I just hate when my teachers are wrong. I'm like, oh, okay, first, chill. But second, good job. You know, and my wife's like, she's trying to teach it in Chinese. Just relax.
Oh,
Is it Chinese immersion?
Yeah, 3 of them are in Chinese immersion.
yeah, I can
It,
understand.
no, it was Jace.
How's there?
He's all right. He's swollen, and he was really salty last night. Like,
Look at his vision.
kind of a bad mood. Yeah, kind of, maybe.
He
Well,
already got his wisdom teeth out.
I got mine out.
yeah. All right.
And mine
Now,
is immature.
we're good. We're good. He just had gotten his braces off, and they said, "Hey, this will be a waste of your $3,000 if he doesn't get his wisdom teeth out." So I said, "Bingo, we'll get them taken out." Okay. These are kind of rare, but we do have a solid that goes straight to a gas in our world, and that's carbon dioxide.
Is it possible to go from straight from a liquid to plasma?
Ooh, I don't know. Plasma is electronless matter.
Whoa, that exists?
Yes, at really, really high temperatures. Okay, so here we go. Sublimation, that's why we have dry ice. It's because it can go from a liquid, and in our cooler, it goes to a gas. Sorry, solid. I'm an idiot. A solid straight to a gas. So since there's no liquid, that's why we call it dry. Then deposition, that's the reverse when the gas goes to the solid. And we don't see that very often, but to make dry ice, it's the reverse. We just remove temperature
Why does dry ice burn your skin?
because it freezes it. It removes heat from you so fast that causes damage to your cells. And then we call that a burn. Okay, there is something that you have to be able to explain about this graph. This is showing you the energy of the system here on the y-axis. And you'll notice the energy to go from a solid to a liquid is roughly that high. The energy required to go from a liquid to a gas is roughly this high. Now that's not drawn very well, but whatever. And it's not to scale, but definitely you need to be able to understand why it takes more energy to vaporize than to melt. Will you think that over just in your own head, kind of quiet? So why is this graph the way it is? Why does it take more energy to vaporize than to melt? Think that out in your head. Don't say anything for a minute. All right.
Excuse me.
That's pretty good.
1 second. Hold on. That is my thing.
What I think you guys should all do on the next test is just study. All right.
Very rude. Quite offended. I did not appreciate it.
All right. So here we go.
Brian, you think everyone's going to
Everyone can. I'll buy you a Little Caesars if everyone can get an A.
No, Little Caesars.
Well, that's the only one I'm going to do because it's cheap.
So good.
Sure, but you got to remember something. I grade the test. Duh.
So you're saying that you'll just like kibosh it to get no.
Yeah, someone's getting a B.
Even if they deserve it,
Now,
you give them a B.
There's someone in here that would gratefully take a B on the next test.
On that test, I did.
All right, here we go. Shh. By the way, the grades are in, and when you saw they're low, it's because you're multiple choice. If you want to come in and redo that, come visit. We'll work some out. Okay, now don't ask me any more questions about this. Why does it take more energy? Okay, Caitlin, she doesn't talk that often. Go.
It's getting rid of all the
All right, good. I wouldn't use getting rid of. I would say it is breaking
Yeah. You got what I mean.
all IMF, and I'm going to say interactions. Yeah, remember a gas, we said that each individual particle had nothing to do at all with the other particles. Remember that?
It breaks their attraction to each other.
Yeah, but a liquid, to go from a solid where everything's like super stuck, we do have to put energy in, but a liquid, there's still plenty of interactions. That's why when I do a belly flop in the water, it hurts. Because the water's still holding on to itself, just not so much I can't go through it. All right, so you are breaking some intermolecular forces to go from here. But from a liquid to a gas, you break every single one of them for every single atom. That takes a lot of energy. This is represented in two different ways on pictures. One is this way, and then the other one might not be next, but I'll get there in a second. It's probably maybe not even on here. Here it is. Now, I'll go back to all that other stuff, I promise. But the other way that this is represented, and it's more typically on this one, is what we call the heating curve. This is for water. And the way you can see it here is the distance of this segment versus the distance of this segment. You'll notice there's way more heat added to vaporize than heat added to melt. Okay, so you'll need to be able to see it on an actual picture. You okay with that? And identify why it's flat? Okay, we'll come back. And most of this is going to say the same stuff.
It takes less time for ice to melt than it does to boil water, right? That's why.
Absolutely. Now, yeah, I'll say sure. Okay, now, we just kind of said this. Heat of fusion, wasn't this one of your matching terms, maybe? It's the energy required to change a solid at its melting point to a liquid. Now, it's kind of weird because fusion means you put together, but it's okay if you think about it in reverse. It was the process of coming together, and the energy would just be a negative sign versus a positive sign. So I know it's weird, but it's fine. It's when we change something to a liquid.
From a gas or from a solid?
From a solid to a liquid.
from its at its melting point. So it's going from a solid to a liquid. So it would be the purple line right here. The heat of fusion, not purple, or sorry, not line, the box.
How far is it to like vaporize market? Is it
You have to get it really hot, whatever its boiling point is.
Can't you do that with anything?
Yeah,
you know,
I could make you boil.
if you do like with the materials we have here?
In this room, I don't think so. The hottest thing I have is a Bunsen burner and it burns at 600 degrees. Let me ask Siri, hold on. Hey Siri, what is the boiling point of mercury?
The boiling point of mercury is 674
Ooh,
degrees
so we
Fahrenheit.
could get close. We could get close.
Just an American Siri voice. Boring.
Okay, nerd.
I have an Indian male. It's amazing.
Of course you do.
And I have an Australian guy.
Okay.
I should get an Australian.
Hey, we're good. We're good. We're good. We're good. We're
Okay,
good.
but there's actually
Oh
a
my
question about
gosh.
this.
Yes.
How come like some things instead of like turning into like a liquid, like they combust instead?
Well, okay. There are some things they will decompose and start to react with the oxygen in the air because that's more reactive. Like the compound they will make is more stable than themselves at that temperature. So it's all about nature trying to stay at the lowest energy possible. So it gets to a certain point, now they become reactive enough, they will react instead of continuing to heat and boil. So it's all about reactivity.
Because people are more likely to like combust
Than to boil. Yep, that's true. Okay, now we're heat of vaporization. That's the energy we have to turn the liquid all into a vapor.
So if you were to put dry ice on this, it would be opposite. Oh wait, no. it wouldn't.
No,
Still be
goes
the
from
same.
solid to
And it will
yeah,
always be
it'd
higher.
basically be 0 for the purple at, and I got to be careful. We can get liquid carbon dioxide,
You just have to.
but it's at 4 or 5 times ATM. So these are things like in a room, temperature and pressure. We put it on a stove. This is what happens. So I mean, yeah, we can have liquid carbon dioxide. We just need something that can put 5 atmospheres of pressure on top of it. All right, we already answered this. Why is the blue much bigger than the pink? And that's because we have to break every intermolecular force to convert a liquid to a gas versus just some of the intermolecular forces. Okay, let me go back to whatever this slide said. It looked important. All right. Oh, vapor pressure. That sure seems out of order. But we'll be all right. Okay. See this? This is where we're supposed to be on Monday. So on Monday, I'm going to give you an opportunity to see if you know the vocab. It's a quiz. I'm going to put it on your grade. You will have 2 chances
To get 99%.
to get 100. I don't know what this is for. It must be me last year saying 99% of students never study or some. I'm sure I was complaining because I'm a whiner. Let's be realistic. Well, who wouldn't?
I love
Okay.
Diet Mountain Dew.
I've never.
All right, now. So I'll give you 2 chances. The first one's on Monday. Someone put a reminder on your phone to remind the group chat at 10:55 p.m. on Sunday. No, don't, I'm joking. But try to remember Sunday,
I'll do it at 11.
Saturday, whatever. You'll have 2 chances to take it. Higher of the 2, that's your grade on that part. It's going in as test points.
That's what the Quizlet is all
Okay,
about.
now hold on. Murray, you heard what I said, right? Garrett? Okay, because like the last time I did something, you're like, I didn't know it was on my grade. So I just wanted to double check. Okay.
Is
Test.
everything on the Quizlet?
It's everything on the Quizlet.
Wait, it's everything on the Quizlet.
Every single thing on the Quizlet.
So if you just get that
Yeah, you get it free.
I guess that's the.
Good. Shut up. I need it for my drink. Shut up and let it happen.
I don't think anyone's complaining. Okay, here we go. So we already said this, but the heat added to the system at the melting point and boiling points go into pulling the molecules farther apart from each other. Okay, what this is saying is really important right here. I think this was on my notes that I took myself. You'll notice at the temperature for phase change, the melting and boiling points, you'll notice the temperature remains constant. That's why, never mind. Does anyone have a water bottle with ice in it? Shake that water bottle. All right. Ellie's water in that hydro flask will stay at 32 degrees Celsius, or sorry, Fahrenheit, until every piece of ice is melted. Once every piece of ice is melted, then any heat that comes in from the outside raises the temperature. But it's why our drinks stay cold forever if there's ice. Go.
So is it not molecules? It's like all of it together?
The whole thing. Now, if you don't disturb it, you'll have colder on the bottom and warmer towards the top. But overall, the entire temperature of the substance stays at the melting point. And that's why when you cook and you boil water, the stove is usually hotter than 212 degrees, but the stuff that you're cooking is never above it until all the water's gone, and then you burn it. So when it says turn it to boil and then down to simmer, you ever read that? It will stay at 212 until every single water molecule is gone, and then you start burning crap because you're not boiling water anymore. You're heating your macaroni and you weren't paying attention and you just ruined the pan and dinner. Okay? So
where's that extra energy going?
it's going into making the things that are close together move apart. It's going to break intermolecular forces.
So it's vaporizing some of the water?
Yeah, it's taking this and kicking it out.
Okay.
Yeah.
Go ahead.
So the energy disperses through the whole thing until there's no more molecules of that left, right?
Yep, and then the energy's got to go to whatever's left, like the pan or whatever's in the pan.
Yeah.
Okay, you guys are great. Thanks for the drink, Cooper. I'm going to change your S back to an N, I think.
No, Cooper, do you think